afternoon, and we are going into the third session, and this will be my final talk for the entire thing. And the thing that is missed was I'll give you some examples. There'll be no presentation anymore. I'll just show you some examples of how to run it with encrypted databases, which I did not cover in the previous part of the session. So in this particular session, I will essentially show you again 3 examples, but this time using function F4, which corresponds to an encrypted database. OK, so the idea is I will show you a binary and a eutectic, and the eutectic will utilize the encrypted thing and a ternary setup. OK, so let's go ahead and try to. This will be a live demo session only, so I'll just. So let's get it here. Let's get it started. OK. All right. So again, these int files are there in the repository. So to run a function F4, you need some additional files, which essentially was detailed in that presentation. So the structure of those files was there, but I will just now point to where you need them in actually doing the simulations. So there is an encrypted TDB's encrypted folder that you need to have in the run folder that you are running the simulation in. OK, so for example, I'm going to now run a system which is a binary. So this is a NINB system. OK, and I'm going to utilize those files that I showed in the morning are required. OK, this is requiring an int file. So let me go and search for the int file first. NINB. OK, NINB is not there, so I have to go to a place and get NINB. Just a moment. OK, let me just navigate and get it so that we have it. OK, let's do this. Oh, we had NIAL. OK, let's copy maybe. Yeah, NINB. Okay. So I have NINB. I will, in the interest of running faster simulations, I will just do a smaller one. And so phases, components, you now all know this is alpha liquid. I'm going to stay with that. These are the files NB and nickel. I mean that will be, so it'll be solving for niobium. And so no restart. OK, alpha liquid. So the all properties are there. Gamma is there. And here you see this key is function F4, which is the encrypted database. All right. So I'm going to do the workflow that is required for the encrypted properties. These phase compositions are tabulated in that CSV file. So I'm going to now open that CSV file and check what is there inside of that. So for example, this is the TDB's encrypted folder. And you see this NINB. So you have these files, they are named composition_FCC_A1. So FCC_A1 corresponds to the one of the phases that you are going to solve for. OK, FCC_A1 and FCC_A1. So I'll just open this file. These are the files that you need to create using your PAN API or TC API, as the case may be, whichever you have. Just 1 second. OK, so this is how the file is. We will just blow it up. So temperature, niobium FCC, and niobium liquid. So you have the phase compositions at equilibrium at the different temperatures tabulated like this. OK, and these are extracted out of Pandat. Similarly, you have the HSN file, which is the Hessian Matrix. So you have just one component in the Hessian Matrix here because you have niobium interaction only. OK, so you have this so with temperatures And yes, well, there will be a problem with this, so we'll use a slightly different system. This is in descending order. I'll just explain with this and I'll just choose a different system. And this is a similar thing for the liquid phase. So for each of the phases, FS, you need to provide the Hessian part of the solver. Okay. Okay, so I've shown you this, but we will do with a different file. That is because I have copied the different thing. Okay, let me go back and get that file for you. Okay. Okay, so let's choose NIAL maybe. Yeah. And hopefully these are in the right order. Just a moment. Yeah, these are in the right order. Yes. Yes, so we will choose this one. So you must take care when you do it that the compositions, the temperatures are in ascending order of. So when you create the file, the temperatures must be as in ascending order. This is required for the GSL spline interpolation that runs inside the code. OK, so typically you can either go from top to bottom or I mean lower to larger or larger to lower, depending on the API you use. But make sure when the files are created that they are created such that they are in descending order of temperature for each of these information that you are going to give. OK, so let's take this. And so this will be required in the place we are running the simulation. So I'm going to presently put it over here. All right. And I'm also going to take the in file that I need. So I'm going to take the particular in file, copy, and take it over to the place I need it. OK. I'll keep it here. OK, so I will go back and import this in file instead of the other one. So let's go here and you have an ILAN. OK, so let's go back and do the same thing. Okay. Phases, composition, these are all the same. I'll keep this the same. And there's a restart on here. I will switch it off. OK, so let's do this first. Let's shift to 0 and then switch it off. And you have the C equilibrium and the C fill again filled from that CSV file that I showed you before. So I will just show you there where it is. And these are the same properties that I just showed. So period, these are all Neumann boundary conditions. And I will import a shape which is very similar to the one that we did in the morning. We will fill a cylinder at the corner. At cylinder, you will put one at the corner, and which will be 5. So this is a binary simulation. I will use the binary flag. The taus get calculated inside. Don't worry about it. And so I'm going to give a 1 Kelvin undercooling because the solidification interval of this alloy is a NIAL system is just 1 Kelvin. OK, so I'm going to use the maximum temperature undercooling that you can have. The equilibrium temperature is 1718. This is 1717. OK, so I'm giving that as the temperature. There's no shift because I'm doing a dendrite simulation. I'm putting some noise and I'm going to write composition. So I'm going to run this as input NIAL, sorry, and filling NIAL, OK, and output NIL. OK, and I'll generate a file the same way that I did before. So let's go back. We will go here. We are making all our folder here. So we'll put a folder name, which is, let's say, NIAL F4, create, and put it over here. So these files will be created. Now, before we run, remember this folder requires the TDB's encrypted files. OK, so what we need to do is to copy this particular folder into this folder that we just created. And I need to copy these three files into a new folder, which will be the TDB's encrypted folder. So you need to make this folder for you. Sorry. So once this is there, the solver will go and search in this data folder the TDB's encrypted data, all right, which will have all of this information that I just showed you. So if you open this, for example, it is the 1717 to 1718 information. OK, so similarly for the HSN liquid and all right. Good. So once this is there, now you're ready to run. You can then go ahead and run. It will still run the Python key, but that is not used anymore. So don't worry about it. So it will just run now. So it starts to run. OK. So you see it's printing aluminum because you're solving for aluminum. It's aluminum and nickel. And so we can again go to that data folder and check what is getting outputted. So let's open. It's here. OK, so 7000. So these encrypted folders, this TDB is encrypted and the .csv files. If you go into the repo, in the repo there is a TDB's encrypted folder with several systems that are already there. So if you want to run, you can just copy the CSVs as I'm doing here, create a TDB's encrypted folder and run it accordingly. OK, so there's a several systems which are already processed and kept for you for testing already. So we will just run. So that it's running. OK, good. So we have done. Now we can go back and do the stuff that we wanted to do. So you see it would have finished. It's finished, right? This is closed. So once it closes, you can actually close the terminal because it will then close the unimportant terminals. And you can open the MicroSim tool. All right. So then you can go ahead and navigate to the in file that you used. OK, before you do that, first remember these are H5. So make H5. So first locate the in file again here. These are H5 files, remember. So H5 files need to be converted to XMF and thereby VTK for running. So you can just load this. And we are running 0 to 20,000. OK, and convert. OK, so it gets converted and then you can open them. So first import the in file. It's always a good idea. And then the data. Okay, so this is growing a bit slower because it's 1 Kelvin undercooling. So if you let it grow faster, you'll get a dendrite at the end of the day. All right. So this is how you can run with the encrypted information, porting it to the solver. All right. Now I'm going to do the same thing with a ternary system. OK. So I closed that. I didn't need to do that. Let it open. So you don't need to close. You can immediately go to the next one just by going back and importing a new in file. So I will do this using again the same. I will now import this nilmo.in file. OK. So it gets copied in. So now I'm going to solve for two components, aluminium and molybdenum. All right. So you see the phase name alpha and liquid are there, and the component are aluminium, moly, nickel. So it will solve for aluminium and moly. OK, and then other things are, let's go them one by one. This is this. This is this. Now you see in the diffusivity matrix there are two components. OK, so that you need to give two entries, and I'm giving alpha. This is a solid, so there is no diffusivity. In the liquid, I have 1.9 and 0.5 E minus 9. OK, so they are not equal diffusivities, they are unequal diffusivities in the diffusivity matrix, right? So there are k minus 1 cross k minus 1 independent diffusivity matrices. So I'm just giving diagonal matrix over here, so only these are populated. All right. Then I can give gamma. And again, I'm using F4 with the thermodynamic phases, and the information about the thermodynamic phases is the mapping is now with FCCA1 and liquid as was with before. Phase compositions. Now you see the phase compositions input is different because now you are taking two components, aluminium and moly. OK, for the equilibrium, and these are taken from the CSV file that you are starting with. OK, these are all the same. Let's import the same cylinder that we had before. OK, and next. See, now it's a ternary flag. I've input a ternary flag to just optimize, because in a ternary what we do is we store the inverse by hand. So you don't have to invert the matrices in situ. If you leave this away, it will do the complete inversion, which is slightly slower than what it should be. All of these are optimized for running now, so I will not touch them. So we are doing a 10 Kelvin undercooling. The 1590 is the equilibrium temperature, and 1580 is where we are running the simulation in. There is no shift, we are doing dendrite, and we have a noise. OK, so I'll do this as input NIALMO F4. Even here NIALMO 4. OK, and I'll give a name here 4. OK, generate files. So again, I'll create a folder just like before. Create here MO4, create, and put the files here. Now, just like before, I need to copy the required TDBs encrypted, so that I have stored it over here. So you see, I will just copy this, and I will create. I'll paste it here. Then I will take the representative files. And I will create a new folder. So this is an essential part because the solver will search for this in the data folder, in the folder that you are running. OK, I need to paste them over here. So before you run, please check what is the order of the temperature, because if it's in the inverse order, so remember it's a ascending order of temperature, and what you have over here is now aluminium, moly, FCC, aluminium, moly, liquid. OK, so how is this done? It is essentially done following the equilibrium solidification path for that alloy composition. So you give an alloy composition and you change the temperature, it will follow the phase coexistence lines, which all have that particular alloy composition as in the tie line. OK, So that is how this calculation is being done. And the corresponding extraction is also done for the Hessian. Now there are two quantities in the Hessian. One is the aluminium, and the second is the MO, and there are three, sorry, aluminium moly. So there are three components in the Hessian matrix now because it's a ternary system. These are the corresponding aluminium, moly, and the aluminium moly interaction terms. And the same thing for liquid. All right. Good. So we are now set. So we can now go ahead. Not trash. So let's run. So it starts to run. So now you see in the folder, you have aluminium and moly getting solved for, as it should be in a ternary system, right? And it will run. So let's again go back and see, follow it in the folder where it's generated. Okay, so let's have it running. So you notice the slightly different speed in execution. This is because you're solving more number of equations now. You're solving for 4 equations: alpha, beta, aluminium, and moly, in contrast to the 3 equations that you were solving before. So it's understandably slower than the binary simulation. But yeah. But we still get done in about 2 minutes, which is what we want in the simulation. Okay, why is it not stopping? Okay, we'll forcefully stop it because I think we didn't give the endpoint correctly. We gave 2 lakh instead of yeah, it's 2 lakh, so that's why it's going on running. But that's okay. We'll just create the next part back. Now we go to post processing and create the H5 to VTK and go to this part here, and you have the NILMO. Choose the in file. Okay, choose the H5 files. Data. Choose the H5 files and go to 0 to 20,000. Convert. Okay, so it converted. Now close it. Then this is the import in file. Import thing. Import VTK. And choose the VTK. All right. So again, this is slightly slower because you're just giving 10 Kelvin under cooling, and you can run it longer to get one of the dendrites that is there. But what you can also see is that you have now concentration of aluminium and composition moly, right? And you can take a plot across the line to show what is going on. This is 99 plot. So you can see the different plots. You can plot aluminium, you can put moly. I'll need to plot it again because this is, so you'll have a different one. Okay, so one is a solvent, one is a solute. That's how it is. Okay, so this is what you can do for a ternary. So a ternary in file can also be generated. And so finally, what I'll do, how much time do I have? Okay, 15:09. All right, so I'll just be able to do one more, which is a UTEC tick. The same UTEC tick we did in the morning, but now this will be done through FNF4. Okay, so right. Okay, wait. So we will use the same thing, aluminium TDB zinc.in. And as in the morning, there are some parameters that need correction, but that we will do. Number of phases component, these will not change. I will not touch that. We will use this. See, next. These are read from the CSV file as needed. So there is something erroneous in the diffusivity and elasticity. So we will correct that first. Beta, all are there. Liquid, there is something problematic. So we will just correct this as we did in the morning. Then we can go to gamma. Now you have three interfaces for the UTEC tick. So alpha, beta, beta, gamma, gamma, delta, and these will be prompted over here. Functional properties, instead of 3 like we did before, we will use 4. Okay, so we increase to 4 over here. And these information as will be there as in the morning. And then you go to next. So as I said in the morning, we have periodic boundary condition in this direction because I want to mimic alpha, beta, alpha, beta, alpha, beta. So in this direction, you will have PBC. And in the growth direction, we will have NBC, which is the Y plus and Y minus directions. Okay. So now we will just do the same filling that we did in the morning. In the interest of time, let's see, we can just copy one of these filling files, import shape. We have it from the morning, so let's do that. Tutorial runs. So you have the UTEC tick aluminium zinc. So we'll just copy this. Okay. And we can go next. We can just go ahead. We'll run it with a shift box like we did in the morning. And you see he complains about tau. So let's go to tau. We'll correct this. And we'll just correct these as the aluminium zinc, but 4. Zinc 4. Zinc 4. And we'll generate in files in a new folder again. Okay, create. So we'll just create here. And just as before we are able to run, we need the TDB's encrypted folder in that particular thing. So we have to get the TDB's encrypted, which are already I have stored it. So I'll just check this guy. Tutorial runs. I'll go into the folder I'm running. I'll copy this. There'll be now, just let me copy first. Sorry. You need a new folder here, which is TDB's encrypted. And paste it here. Now you notice there are 3 phases. So there is a composition file for the FCC, composition file for the HCP. These are the 2 solid phases. whose compositions will be tabulated against the liquid phase. So if you open this, so you see there is X zinc with okay, there might be one issue with running with this. These are with zinc. Nevertheless, I'll just tell you the workflow. Okay, no, maybe I'll just copy it from another elsewhere. Just a moment. The thing is, it's tabulated against zinc, but it'll be solving against aluminium. So they need to be in that order. You need to provide the right compositions in the CSV file. So we'll get it. I have it stored in the right place. Yeah, this is the place. We'll just go here, copy these. Okay. Close this. Okay, so let's paste these guys. Replace, 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 replace. Okay, the difference is you will see now. You see it's an aluminium because aluminium is the component that is going to be there in the in file. Okay, so I mean it can run with zinc as well. It's just that you need to provide consistent equilibrium compositions and filling compositions. So since I have already filled with aluminium compositions, I just wanted this to be consistent, which will then be all okay. So this is now for so these are FCC compositions in equilibrium with liquid. Similarly, HCP compositions in equilibrium with the liquid, because in eutectic there are three-phase equilibria. So you have alpha, which is FCC-A1 in equilibrium with liquid, and HCP in equilibrium with liquid. So both of these have to be provided in the temperature range of interest. Similarly, you need to provide Hessian matrix, the Hessian matrix, as a function of temperature at the eutectic composition. Okay. For HCP and FCC and the liquid phases. Okay. So 3 files. So in total, you will have 5 files for this 3-component thing. So now we are ready to run. Okay, so we have the TDB's encrypted folder. So now we can just go ahead and run. Okay, so it starts to run. So now you have alpha beta liquid being outputted along with the composition that you're solving for, which is aluminium. All right. So we can go and follow as we were doing before. Let's close this fellow first. Close. Let's go here. Let's put it sideways so that we can see it. And then go ahead. So eutectic aluminium zinc. All right. So as in the morning, you see this shift file gets written because it's run with a shift algorithm. You'll keep shifting the domain as the thing, and you will keep a record of that so that you can rebuild the data later on. So in the repo, this aluminium zinc that is uploaded is with the zinc composition. So you need to just open it in Excel and do 1 minus the column thing so that you get aluminium compositions, and then fill corresponding aluminium compositions in the in file that is uploaded. That's the only change you need to make. All right. Good. So it's done. Close terminal. And we will open the MicroSim tool. We can close this. We'll run this. Locate. input. Okay, pub and go to here, data, open. All right, everything else is the same. Converted. Then all you need to do is to import the INF file first. Then the data. And as in the morning, I've run for a short time. So you will have a short evolution, but this is the same evolution you will see in the complete form later in the solver. So I will just show you that and close my session with this. So for example, you can go here. The complete run looks very similar to F3 as it should. As I claimed before, F3, F4 are all equivalent. It's just how you're going to take data and input into your system. So let me just open here in ParaView. So there is something that I have already run for this, so you have it stored. So just as you saw in the morning, you have a result which is looking very similar to the F3 result. And so essentially, I have just taken information. The first F3, it directly reads in the functions and it computes whatever is necessary for the parabolic expression. Whereas here, you are taking in the Hessian, which is calculated from a separate code written into a file, and that file is read in. So that is mimicking how you would do it in a encrypted TDB. Also, although aluminum zinc is not encrypted, I have taken the information following the workflow of an encrypted database and read it into my solver and done the relevant calculation. All right, so with that, I think I have given you a taste of how to use all the different thermodynamic coupling strategies for different systems. And I think that was the aim of this particular discourse, to just show to you or demonstrate to you that thermodynamic coupling of any system is now possible in a multi-phase, multi-component system for the grand potential part of the release. So the grand potential solvers are multi-phase, multi-component compliant, as well as they can couple to thermodynamic databases in a form that I have just shown you. So now the floor is open for questions. So anything that you would like to ask, please go ahead. There's a question? Okay. Will the recording be available? Oh, yes, it will be. Yes, we can do. Muhammad Umar, yeah, we can do any number of components. The system is, it's just as if you just put the, if you get the CSV file with the required information, the function 4 can directly take in any number of components. No issues. Hey, there was no sound, is it? No, there was. No. Previously, when you were speaking, the chat was okay. Okay. Questions? More? So we can collect all the questions in the final session, and we can go have a complete discussion on it. In the interest of time, maybe we can just. We still have 7 minutes or so, right? No, we have 3:45. Yeah, we have 15 minutes. So if you have questions, please go ahead.
Hello.
Yes.
Yeah, my name is Muhammad Umar, and I'm currently doing my PhD at Karlsruhe Institute of Technology, probably where I have a lot of legacy of Abhik Chaudhary there, and I can, yes, I have gone through the papers and the basics that have been a part of your PhD thesis as well, Dr. Abid Chaudhary, and I am actually working on the dendritic growth right now with the four-component system. And
Okay.
the question, yeah, the question is it possible with this MicroSim that we can do the four-component system with the dendritic growth at different at temperature regimes? I mean, if, for example, I want to mimic the solidification process starting from the liquid up in the range where it first the dendrite grows and the complete liquid becomes solid into delta ferrite, and then that delta ferrite gives the peritectic reaction and transformation. So we have the capability to take into account all of these processes, right?
Okay, so I'll go ahead into steps. So quaternary system, we can do it in the same workflow as I showed you. In the CSV files, I'll just open it just for demonstrating. Just 1 second. Not this, sorry. Let me open. This is the TDB is encrypted. So let me just open the ternary one, which will give us will give you an idea of how it will look for the quaternary one.
Yeah.
So let's open this. Okay, so you see, this is how the composition file looks like, and the HSN file will look like, which is the Hessian matrix. Okay, and let's now the composition file for the quaternary. Here you have 3 components, so you have 2 independent, aluminium and moly. Okay, aluminium moly is solid, aluminium moly liquid. So you're able to take 3. For quaternary, you just have to provide aluminium moly or any other component that you are interested. Aluminium moly, the other component for the liquid phase as well. This information you need to extract from the pandat databases and input in this format. Similarly, the Hessian matrix has to be done in the same manner. You have to there will be number of components will be again k-1 cross k-1. So here it was 3 components, so 2 cross 2 matrix. There it will be the 3 cross 3 matrix. So you need to provide the 3 cross 3, all the components of the 3 cross 3 matrix. First the diagonal and then the non-diagonal components in a upper part of. So it's the upper part of the Hessian matrix that you need to provide, because Hessian by nature is a symmetric matrix. All right. So that is what you need to provide in this file. Once you provide this file, in the in file, the number of components have to be set to 4, and you need to point that, and you need to use function F4. It should all run just by itself. Okay. So that will essentially have the delta ferrite growing from the liquid. All right.
Yeah.
And presently in the MicroSim module, delta ferrite growing from the liquid happens in the particular MicroSim GP model right now. It happens at 2 possibilities exist. One at isothermally, it is at a given undercooling, or you can have non-isothermal where you have directional solidification. There will be a module in the future where you have continuous cooling given by so the entire microstructure will be essentially following a temperature path given by the latent. So you will be cooling down, extracting heat with a given rate, and the latent heat release will sort of increase the temperature of the domain. So this part where the I was showing this in the morning to you for the open form module. The similar type of simulation will be possible with the GP module as well very soon in possibly one of the sub releases. So we wanted to include this, but just because of the time issues, we didn't include this in this release. So cooling of the temperature as the microstructure evolution goes on it will also be part of the software very soon. In this part of the software, that means MicroSim GP. It is already available in the open form module, which is going to follow this session. You will see some examples of cooling down as the temperature is evolving and the microstructure evolving simultaneously. That is something that you will see in the following lecture.
Yeah, thank you very much, Professor Abid.
Okay, thank you. Okay, I guess we can collect the questions, Swapnil. You can collect the questions and have it in the next session. Here, I mean, in the final session, there'll be some time. So we will ask all audience questions who had questions to chat them here, and we'll collect them and have them addressed at the final part of the session.